Let's continue our lecture video discussion in differential calculus under the topic application of the derivatives, time rates. Now let's continue answering problem number 5. Here, a man 1.6 meter tall is walking away from a lamp post at the rate of 1.10 meter per second. If the lamp is 6 meters above the ground, find the rate at which his shadow is lengthening, and B, the rate at which the tip of his shadow is moving. So here is our drawing. So here, this man here is 1.6 meter tall. And the lamp post is 6 meters from the ground surface. Okay, so 6 meters. And the man is walking away from the lamp post at the rate of 1.10 meter per second. Now, first, the first step is identify what is changing and what is fixed. Obviously, what is fixed here is the height of the man and the height of the lamp post. What is changing, therefore, is the distance as this man is traveling and the distance from the tip of his shadow to the lamp post. That is our number 2. Step number 2, assign variables to those that are changing and appropriate value or constants to those that are fixed. Now, let's put here a variable x e So the distance traveled by the man is x. Therefore, his rate here as he is traveling is dx over dt. That is 1.10 meter per second. So the man is walking 1.10 meter per second. Now, what is being asked? It says there, find the rate at which his shadow is lengthening and the rate at which the tip of his shadow is moving. Now, this might seem confusing at first. How can they be different? Well, let's explain it here. So, at this position, the man's shadow is from his from where he stands to this tip. So at this tip of the beam of light. Okay. Now, the first one, the rate at which his shadow is lengthening, it's talking about the length of the shadow. If it's talking about the length of the shadow, where do you think is the point of origin of that length of the shadow? So obviously, this is the tip of the shadow. The point of origin of that length of the shadow is none other than at where the person stands. So if the person is standing here at this portion, so definitely the tip of his shadow is generated from where he is standing to where the tip of his shadow is. So that's how the light is. So that's how the length of his shadow. So as this man goes farther away from the lamp post, his shadow is lengthening. So that's why the length of the shadow is a variable. It increases as the man goes farther away from the lamp post. Therefore, let's assign a value here as y. or let's assign a variable y. So that is the length of the shadow. Now it's asking for the rate at which his shadow is lengthening. Therefore, it's asking for dy over dt. Okay. Next, at letter B, the rate at which the tip of his shadow is moving. Yes, the tip of the shadow, this portion here, is moving as the person is walking. So again, if the person is at this point, where is his shadow, the tip of his shadow? If this is the beam of light, of course, the tip of the shadow is located in this portion. Now, the problem says that the man is walking away from the lamppost. So originally, the man is standing here near the lamppost. So, if the beam of light hits the man, so obviously the tip of his shadow is located almost at the post. So what does it mean? It means the origin of the measurement of the movement of the shadow is located in the lamp post. Meaning, the man is standing near the lamp post. So the man is here. So the tip of his shadow is located here. As he is walking farther away from the post, so the tip of that shadow keeps on moving until it reaches this point. So what is now the length of the distance that the shadow has moved? If that is the case, the distance of that movement of the shadow is distance z from the lamppost to this tip here. And it's looking for the rate at which the tip of this shadow is moving. Therefore, it's looking for, yes, it's looking for dz over dt. Okay, so I guess we have put necessary variables and values here. So let's solve first letter A. So what's being asked on letter A is dy over dt. Now let's have the third step. Create an equation relating all the variables and constants in step number 2. So what equation can we use? Now looking at the figure, what can you observe? It's a triangle. So therefore, we can use the properties of the triangle. So we have there the triangle there, and this is the height 1.6, and this is the height of 6 meters. Now, if this is dy, what can we use here? So this is x and this is y. There. Now, using the property of, or by similar triangle theorem, so we can observe two triangles here that we can use. The first one is this portion. Let's change the color. This portion here. So this is my first triangle. Okay, so that's the first triangle, and the next triangle that I could use in the similar triangle theorem is this portion here. There. which is this is also x. And how about this portion here? Oops. So this is 6 minus 1.6, and that is equal to 4.4. So the triangle here has 4.4 height, and then the base x. Then we have there 1.6 height, and then the base y. By similar triangle theorem, we have it y, the base over base, y and x are both base of the triangle, equals the height. So make sure it's the height wherein y is the base. So the height 1.6 all over 4.4. Then we have there 4.4y equals 1.6x. Then let's derive this. This is 4.4 dy over dx. That is equal to 1.6 dx over, it should be dt. Okay, so dy over dt. And this is dx over dt. Now, knowing that dx over dt is 1.10, therefore let's substitute the value. 4.4 dy over dt is equal to 1.6 times 1.10 or 1.1. Therefore, dy over dt is equal to 0.4 meter per second. So that is what is being asked. So knowing the rate at which the man is walking, we were able to get also the rate at which the length of his shadow, the rate at which his shadow is lengthening. Okay, so this is for example number 5, letter A. Now for letter B, at letter B, it's asking the rate at which the tip of his shadow is moving. So we are looking for dz over dt. dz over dt. Again, what equation can we use for step number 3? We can again reuse the similar triangle theorem. So this is our triangle. So using the similar triangle theorem, what can we use here? So this is 6 meters high, then this is 1.6 meters high. So therefore, if this is this is y, and if this is z, therefore, what triangles are we going to use as similar? So we can use this portion. The smaller one, we're going to use the dy, and the bigger triangle. Alright, so the big triangle and the small triangle. So by similar triangle theorem, STT, so there, by similar triangle theorem, so we have their base over the base. So let's use the bigger triangle. The first one, the z over y, base equals height if we have started with the bigger triangle as the base, then let's get the bigger height as the numerator. 6 over 1.6. So we have there 1.6z equals 6y. 1.6 dz over dt equals 6 dy over dt. Then 1.6 dz over dt is equal to 6 times, what's our dy over dt a while ago? It is 0.4. Therefore, dz over dt is now equal to, that is 1.5 meter per second. So that is the rate at which his shadow, the tip of his shadow is moving. Alright, so that is for letter B. Next, let's solve for the example number 6. Two ships, A and B, are sailing away from point O along different routes such that angle AOB is equal to 60 degrees. Ship A is sailing at the rate of 25 kilometers per hour. Ship B is sailing at the rate of 30 kilometers per hour. How fast is the distance between them changing when OA is, or the distance OA is 15 kilometers and the distance OB is 18 kilometers. So to visualize, let's have this drawing here. So here we have there, let's say this is ship A, so it's moving from point O to towards that point, and then this is ship B. So first, identify what are changing and what are fixed. So what is fixed here is the position of point O. It's fixed. So let's say that is the port to where the two ships came from. And then it's sailing away. They're separating from each other. Ship A and ship B. Now, how fast? It's asking for how fast is the distance between them changing when OA is equal to 15 kilometers and OB is equal to 18 kilometers. So, obviously, the distance of A is changing, distance B is changing, and the distance between them is also changing, wherein as they move away, farther away, the distance between them becomes greater. So let's name this as X. So this is X, which is 15 kilometers, and that is changing. It says there, ship A is sailing at a rate of 25 kilometers per hour. So this is dx over dt is equal to 25 kilometers per hour. Next, we have there, let's name this as y. So this is y equals 18 kilometers. And again, this is changing. It's changing. So this is dy over dt equals 30. So it says here, B sailing at the rate of 30 kilometers per hour. Another one is this portion here. Let's name this as z, and which is also changing, dz over dt, and that is what is being asked. How fast? is the distance between them changing. And don't forget, we have here angle 60 degrees. Okay, I think we were able to assign variables and constants. Next, number 3. Create an equation relating all the variables and constants in step number 2. So what equation can we derive from this situation? Well, we can use the cosine law. So, cosine law. According to the cosine law, so if you're looking, if the angle here is given, okay, therefore, this is the opposite of that angle, which is we will put here z squared equals the adjacent to that given angle. So these are the adjacent sides. We have there x and y, and minus twice of those adjacent sides, then cosine of the angle, so angle 60 in that figure. Then put in the values. So we have there z squared equals x here. Well, I think let's not put in the values first. Let's derive it first before putting in the values. So let's derive it first. As for the step number 4, differentiate the equation with respect to time. Well, of course, if we substitute the constant immediately, what will we get? We will get a value of 0. That's why we need to differentiate it first before we substitute the values of the constants. Okay, so we have there 2z dz over dt equals 2x dx over dt plus 2y dy over dt minus 2, let's bring out cosine 60 here, because 60 degrees is fixed. By the way, I forgot to mention, the angle here is fixed because as the sides keeps on lengthening, the angle still remains the same. Right? Then, we have there x dy over dt plus y dx over dt. Okay, then after you differentiate them, you now substitute, we will now substitute the values. So this is 2z dz over dt, that is equal to 2x, no, the value of x here is 15, dx over dt is 25, plus 2 times y is 18, dy over dt is 30, minus 2 cosine of x 15 dy over dt. I forgot to put, that's correct. So that is 15 dy over dt is 30 plus 18. So we need to always pay extra careful attention to the values that we are putting in. One mistaken number could ruin the entire equation and thus make the answer incorrect. So that's why we need to always take second or third checking before we proceed to the calculation. Okay, so we input this and the calculator, the value for 2z dz over dt is now equal to 930. Well, we cannot get this value yet because of the fact that we don't know yet the value of z. So, how can we determine the value of z? Now, look at this equation here. We can use this equation to find the value of z. Since the value of x and y is given, then we can locate the value for z. So, let's simplify this one first. dz over dt is equal to 930 over 2z. So, this is now equation number 2. Now, at equation number 1, we have there z squared equals x squared plus y squared minus 2xy cosine 60. X squared is equal to 15 squared plus 18 squared minus 2 times 15 times 18 cosine of 60. Therefore, z is equal to 3 square root of 31 kilometers. Then, substitute z, the value of z to equation number 2. Therefore, dz over dt is equal to 930 all over 2 times 3 square root of 31. So the value now of dz over dt is equal to 27.84 kilometers per hour. So that is for sample number 6. Now for our last example, example number 7, for time rates. Water is flowing into a conical vessel 600 mm deep and 250 millimeters wide across the top, at the rate of 200 cubic millimeters per second. How fast is the surface rising when the water is 400 millimeters deep? So we're talking about conical vessel. Conical vessel that receives water. So that is our drawing. So water is flowing into this conical vessel. And what is the rate? Well, it says there, water is flowing into a conical vessel 600 mm deep. Okay, so the vessel is 600 mm deep. Okay. So we have there 600 millimeter deep, 250 millimeters wide across the top. And water is flowing at the rate of 200 cubic meter per second. So Q is equal to 200 cubic millimeters per second. How fast is the surface rising when the water is 400 mm deep? So this is the water, the height of the water. So what it is asking is how fast is the surface rising when the water is 200 mm deep. So here, this 400 mm here is our small h. Let's name this as the big H. Therefore, dH over dt is equal to question mark. And Q here is the derivative of volume over dt, that is 200 cubic millimeter per second. And we're going to look for dH over dt. Okay, we're done with steps 1 and 2. So again, for step 1, the one who is constant is the dimension of the vessel, because as time increases and as water continually flows into the vessel, the dimension of the vessel remains the same. What is changing is the height of the water. And what else? What's changing here? Well, it's also changing in the value of the radius. If you observe, the radius increases as time increases. Okay? Create an equation relating all the variables and constants in step number 2. So what we are going to use as an equation will be volume is equal to 1/3 pi. So what are we going to use here? The volume of the conical vessel or the volume of the water? If we are to take the volume of the conical vessel, therefore the volume becomes constant. So here, in this problem, we are going to take the volume of the water. Okay. So this is changing. That is a variable. That is also a variable. This is also a variable. There's 3 of them. We need to eliminate one variable so that in this equation, we're dealing with only 2 variables. So how can we eliminate one variable? Anyway, which variable are we going to eliminate? So we cannot remove that because it has a value there. We cannot remove this because it is what is being asked. Therefore, we need to remove radius. Now, to remove the radius, we need to use another equation wherein that radius is connected with the other constant and variables. So what can we use? So we can use here a similar triangle theorem again, because if you look at this intently, this is the cross section of the this conical vessel, this cone. Okay. So therefore, this becomes the radius, and this is the bigger radius. So this is the radius of the conical vessel, which is 1/2 of 250. So 1/2 of 250 is 125. Then you have here the height of the big and small triangles. So this is 600 mm and this is h. We are using constants and variables here. The variable r and h, the constants 125 and 600. So again, by similar triangle theorem, we have there the radius, height, the smaller radius, smaller height, big radius, big height. So r is now equal to 5h over 24. And let's name that equation 3. Then substitute equation 3 to, oh, it's not equation 3, it's equation 2. I've been used to having this at equation 3. Yeah. So substitute equation 2 to equation 1, wherein equation 1 is v is equal to 1/3 pi r squared h. So v is equal to 1/3 pi, r is 5h over 24 squared h. So v is equal to 1/3 pi, this is 25h squared all over 576 each. Then v is equal to 25 pi all over 1728 h cubed. Now let's derive this. This is now dv over dt. This is now step number 4. 25 pi over 1728. Then we have the 3 h squared dh over dt. Then dv over dt has a value, and that value is 200 cubic meter per second. So let's put here 200. 25 pi over 1728 times 3. What is h? The value of h here is at 400 mm. See, after we just differentiated, that's the only time we substituted the value of h in the equation. Now dh over dt now is equal to that is 9.17 times 10 raised to the power of negative 3 millimeter per second. Or you can have the value dh over dt is equal to 0.00917 millimeter per second. So that is our example number 7. Okay. So that's all for the discussion of time rates.